we're going to talk a little bit more about the difference quotient, and I'm going to give you an alternative way of looking at it. Okay? So let's say we had a function like this, and we have a particular x value here. Now before, when I did the difference quotient, I had x of 1, x of 2, so two different ordered pairs. So instead of using x of 1 and x of 2, I'm going to use x and x plus h. So x of 2 is x plus h. So it's taking x and then going h units, a little bit a ways from that. And then what you're going to do is get these 2 points on the graph. So this point is just x, f of x. And this point here is x plus h, f of x plus h. Right? And then the average rate of change would be the slope of the line that goes through those 2 points. And that's the difference quotient. The difference quotient gives you the average rate of change. It's going to be the difference in the x values, or the difference in the y values. So f of x plus h minus f of x. Okay, and then this would be x plus h minus x. So that's the difference in the y values over the difference in the x values. And we see already we can simplify this here and make our difference quotient here. So the x's cancel out, and our difference quotient would be f of x plus h minus f of x all over h. Okay? And this is going to be kind of our alternative way of looking at the difference quotient. And let's do an example to show you why this might be useful. Okay? So remember in the previous video, we had the height of a rock at time t after you dropped it off of a cliff, and it was given by the following function. Okay, so what I'm going to do is I'm going to set up the difference quotient here for this particular function. If I do that, what I'm going to get here will be h of t plus h minus just h of t, and all of that divided by h. So it's basically putting in the x plus h and x into h, but of course h is not h of x, it's h of t. Okay, so it looked like this. And so basically I'm putting t plus h into this function. And when I do, I get negative 16 t plus h squared plus 1024. So that's just this part. And then I'm going to subtract h of t, which is just the regular function. So that's negative 16 t squared plus 1024. And then all of this will be divided by h. Okay? Well, I'm going to be able to simplify this here. I can expand the t plus h out by foiling, and I'll get negative 16 t squared plus 2th plus h squared, and then I got plus 1024, and then I have minus, and what I'm going to do here is I'm going to distribute the negative sign, so I'll have plus 16 t squared minus 1024. Okay, all of this over h. Okay, so now I can distribute that negative 16. So I'm going to do that now. Negative 16 t squared minus 32th minus 16h squared plus 1024 plus 16t squared minus 1024, and all of this is divided by h. And so now we're going to get a whole bunch that'll cancel out. The negative 16t squared, positive 16t squared, and then the 1024, negative 1024. And that leaves me with just this portion here. That's negative 32th minus 16h squared all over h. And what we find here is that the h's, you can factor the h out and cancel that out, and you're left with just negative 32t minus 16h. Okay, so now here's why this is useful. If I wanted to find the instantaneous rate of change at this time, I couldn't do it, because in this difference quotient here, your h would be 0, right? It would be at that instant. There would be no interval. This would be a 0 on the bottom. Okay? And so, but I could get close to the instantaneous rate of change here by moving h closer and closer to x, right? And that would be ordered pairs that would be getting closer and closer, and then the average of those would eventually be equal to the slope of this tangent line at this point. Okay? And so really letting this ordered pair get closer to this is a matter of letting h go down to 0. And then when it's actually equal, when h is 0 and it's equal to x, you would have the instantaneous rate of change. Well, in this case you couldn't let h be 0 because you'd have a 0 in the denominator. But when you write it all out like this and simplify, you actually get rid of the denominator and you're left with this. And so what I can do here is I can let h go to 0 in this expression, and this whole term would go to 0, and I'd be left with negative 32t. And this would actually give me the instantaneous rate of change at time t. Okay? So we can say when the rock hits the ground, that was at t seconds. So when t is equal to 8, that's when the rock hits the ground. Our difference quotient here is going to be negative 32 times 8. And we calculate that, we get negative 256 feet per second. Okay, and this isn't just any difference quotient. This is a difference quotient when we could put here when h is equal to 0. Okay? And the idea here is this is the instantaneous rate of change. Even though we can't put a 0 in this denominator, this thing would be 0. You get 0 over 0. By simplifying the algebra, we're left with an expression where you can place 0 in there. And so if we let h go to 0, there's no longer a problem. This expression goes to negative 32.2. So this idea of letting h go to 0, this is known as taking a limit. Okay, you're not evaluating this expression at 0. That would be undefined. But we could let h go to 0, and as it does, this expression goes to negative 32t. And then we can use that at whatever time to find the instantaneous rate of change. And if you look at what we did before, this actually works with what we did before, because we did it at we calculated the average rate of change in those last 2 seconds from 6 to 8. We got negative 224 feet per second. And then from 7 to 8, in that last second, it was negative 240 feet. And then 7.9 to 8, so in that last tenth of a second, it was negative 254.4 feet. Well, at 8, it's negative 256 feet, right? So this makes sense. These average rates of change are approaching this instantaneous rate of change. And so that's how this difference quotient is helpful. And we're going to be using that in the next chapter to calculate the derivative. And the derivative is actually the instantaneous rate of change of a function at a particular point.